record it. Right. So again, yes, one of the things that I mentioned last week and I've been mentioning from time to time in the course is the whole idea that what we're doing is trying to model the behavior of something that's something we're designing or something that we are analyzing. We are typically, as I mentioned last week, we are typically given something to solve as engineers or to fix, all right? And what you know about the particular situation at hand are certain things about how it behaves or is expected to behave, and certain limits, and you kind of work around that. The thing about it is that the description, for instance, if you go back to kind of the electronics course that we're doing as well, if you've given a circuit and you have a sort of already sorted together circuit and it isn't working, at that point in time, trying to figure out why is going to be tedious. And then if that sorted version was something that you made to solve a particular issue at hand, and you went through, you designed the thing on paper, you got it seemed to work good on paper, you got the components, you put it together, you sorted it up and put it in a case and everything else, and then hook up the wires, and then at that point in time, you find out that it's not working. That is a little bit late in the game. So what we try to do always is to find some way of modeling the behavior in an intermediate stage so that if certain things start to show up even before you reach the stage where you're putting it together, you can take some sort of corrective action. And the Laplace transform in our particular situation is one of those sort of stepping points that we have, because what it does, it converts the description of whatever we're designing from something that is described in time with integrals and derivatives and so on into something that is described as a function of another variable. It's in another universe, but we get rid of the integrals and derivatives, and we only have to deal with multiplication, division, addition, and subtraction, and so on. So, and while we are there, last week we saw you could look at certain things already that we spoke about, which were like the poles and the zeros. And remember me telling you that the zeros are those values of the system that cause it to shut down, and the poles are the values of S, which cause the system to want to blow up or go to its maximum value. And it's that balance of the poles and zeros that make the system do exactly what we want, neither shut off nor go to whatever extreme it has. So one other thing that we like to do in system design, even without reaching, sometimes what you have is that you know that the system is supposed to start at some particular value or some sort of behavior. It could be a voltage, it could be a speed of rotation, it could be a temperature. It's supposed to start at that value, and then no matter what you do, it's also supposed to not exceed some other value at the end. In other words, there's a maximum value. So in terms of the more scientific language, the system is supposed to have some initial value where it starts. It could be at 0 or something else. And it is supposed to reach some final value when you use the system. And that value, of course, we could call just the final value itself, or typically the steady state. And remember last week talking that the system itself, usually if you have a system response, it does something. I'm just drawing it very simply here. But from the time when you turn it on to some point, the system is moving from its initial value, right, the starting point, is changing, and then it reaches some final value or some steady state. And this particular zone here is what we call the transient state. Transient just means changing. All right, so what you do is that what you would like to know is, first off, what is this? You have the system design, but you haven't started to make anything, put it together in hardware or software or whatever it is as yet. But you would want to know this, and you would want to know this. Sometimes this behavior may do all over the place, all right, but it has to land up at some value. We will talk about this particular behavior in a subsequent lecture. But for our purposes, you want to know where it's starting and where it's ending. All right? So, and this makes use now, you could do one or two things. What you could do is that you could have the expression for yt, right? Yt equal to some function of t. And then if I wanted to figure out what it is doing, I could let t equal to 0, and that will give me y at naught, which is a starting point. And then if I wanted to see what it's doing when the system has been on for a little while, in other words, a steady state, I could have y of t at t going to some very large number. So I can let t get very big and then see what f of t is, right? So f of naught will give me my initial value, and f at infinity, t equal to close to infinity, will give me my final value. The thing about it though, is that this business here, this here is usually a differential equation, or even in some cases an integral differential equation, right? Of course, if you have an integral sign and a differential sign, what you typically do is to take this particular equation and you take the derivative, so you convert it to a pure differential equation. So like an RLC circuit has both integrals and derivatives in it, and what you would do is that you take the derivative once again, and you get a second order differential equation, and then you try to solve it. As we saw last week, those aren't easy to solve, and to go all of that to get back into to solve y of t. Well, what we did was to take the Laplace transform of this, right? Laplace transform of y of t, and this would now give us our y of s. And in here now, in this domain, the S domain, maybe we can look and see how this business of the initial behavior and the final or steady state behavior, what happens inside of in the S domain. And that way, because we know here is just addition, subtraction, multiplication, and division, it's a lot easier than trying to figure it out on this side, okay? And this is where these two theorems come in, which is the final value theorem and the initial value theorem. And then if you look at, if I were to ask you just quickly, this is a little aside, if I give you something yt equal e to the 3t cosine 100t. Cosine 100t is a cosinusoid, right? So, you know, it's going to do this kind of behavior. All right, 100t is, well, 2 pi f is 100, so you can figure that out. E to the 3t, is that an increasing or a decreasing exponent? This bit here. Is that increasing or decreasing as t goes on? Anybody? Just to make sure I'm not talking to 56 sleeping people. Increasing or decreasing?
Increasing.
Increasing, right? So e to the 3t is an increasing exponential. So it's going to do something like that. So if you multiply this by that, what you end up getting is an increasing function. So it's going to look something looking like this, right? So the cosine, it starts and it keeps and it's going to get bigger and bigger and bigger and bigger. This now does not converge, right? In other words, the value will keep getting bigger until it reaches the limit of whatever the system can handle, all right? So this does not converge. In other words, it does not settle down to any sort of value. On the other hand, e to the minus 3t does converge. And eventually, as t gets very big, this bit here, as t gets very big, this eventually goes to 0, so that in the limit, yt will eventually end up being 0. In other words, the final value of yt is 0, right? This final value, the previous one that we have, because it does not converge, it really does not have a final value, right? If it's an electronic circuit, the final value could be whatever the saturation value for the circuit is, however close it gets to the supply voltage. If this is a motor, it will go as fast as the motor can rotate. If this is a valve opening some gas flow or something on a process plant, it will open the valve as large as the valve can open and stay there, right? So it's uncontrolled. This particular one is controlled. Whether you actually want it to shut off or not is a different problem, but at least you know as time goes on, eventually this will settle down. And then you have this particular one, e to the minus 0t or e to the 0t, whatever it is, this is 1. So this particular one now does not have really a steady state value. It does not converge, but it is, in this case now, is oscillating between plus and minus values all the way. So this doesn't have a final value either, but it may be something that you can use, right? There are things like this. We know sinusoids, and we make use of sinusoids all the time in AC power. This is what our AC power system, the voltage looks like. In electronics and so on, we have signal generators that give us this kind of thing, right? So it is not something useless, but it's something that you have to be careful with. And again, the thing is that the value here, it does not converge. It's not going to settle down to some final nice stable value here. It's going to go plus and minus all the way through. So let's see now how this initial value and final value theorem goes. If you have done this in 1016, fine. This will serve as a reminder. All right. Yeah. So just remember, I can't see the chat here. So if I ask a question and you respond on the chat, because of the screen I'm watching, I can't see the chat at the same time. So you have to tell me. All right. Yeah, so this may be revision. If not, just use it as such, but trying to put it in the context of things that you'll need later on. So a system has a transfer function of this particular expression here. And remember what the transfer function was? The transfer function is the Laplace transform of the impulse response. Remember we did that last week. Right? So what is the steady state value of GT? GS is this. So the steady state value of this, that is as t goes to infinity or t gets very large, what does this system do? Well, of course, one way of doing it is to now take the inverse Laplace transform of this. So you can break this up into partial fractions, solve for the coefficients, get GT, and then when you get GT, you let t get very large, go to infinity, and see what it does. All right? However, why do that? The purpose of the Laplace transforms and these kind of things is to enable us to do this sort of assessment without having to come back into time as yet. We want to do as much manipulations as possible in the Laplace domain, satisfy ourselves that things are really working exactly how we want it or close to how we want it, and then we return to the time domain, okay? So this is where, as t goes to infinity, we make a use of something called a final value theorem. It is a property of the Laplace transform, and the statement of it is simply here, that if I have a function gt, first off, the function gt must be able to have a Laplace transform GS. Okay, so you're making an assumption here. But if you have some function of time t, and you want to find out what is the steady state value of the function t, in other words, what is the value as t goes to infinity, then in the Laplace domain, what we do, if gt has a Laplace transform gs, then as t goes to infinity, if we find the limit of s multiplied by gs, you have to remember this little bit, you take the limit of sgs as s goes to 0, as s goes to 0, notice that, right? So that's a sort of dual behavior here. As t goes to infinity in time, the behavior in the Laplace domain is s going to 0 of s times gs. Okay, that is a statement of the final value theorem, and this here will give us the final value of the system. So, for instance, we had one which is 1 over s into s plus 1, right? That is gs. So, what we want to find is the final value of that. In other words, what happens to gt as t goes to infinity? According to this, we have to multiply this by s and set s set s to 0. If I do that, set s to 0, notice that the final value of that system is 1. So in other words, as t goes to 0, the final value of the system is 1, and we are evaluating that all in the Laplace domain. To verify, if you were to find the inverse transform of the expression here, you would get 1 minus e to the minus t. And if you want to verify as t going to infinity, as t goes to infinity, e to the minus t goes to 0, so that the final value as t gets very large, gt goes to 1. And we've confirmed that here, right? So we confirm that here without coming back from the Laplace domain. Fair enough? Yeah? No, maybe? Was this something that you all met in 1016? Just let me know if so I'll have an idea what's going on. You met it before? Was this something that you all met in 1016 already, or not?
Yes.
Yes, okay, great. Right, so you touched on it, well, good. So this is, again, a little bit of revision. Right, so the final value theorem, limit of s gs as s goes to 0. What about the other one now? What is it, the transient value, the initial value of gt? In other words, this is maybe put initial here, right? Rather than transient, because the transient means a changing value. So this is not quite correct here. When the system is immediately switched on, I don't know what the system is, but when I turn it on, you remember when we saw when you turn on the system, you're putting a step response onto it. What does the system do? Does the system try to immediately go up to some big value and then come back down? Does it gradually go up and so on? What we want to know is just at the point where I turn the system on, what is this system doing? In other words, at t equal to 0, or maybe just a little bit after t after 0, what is the value of the system at that point in time? Again, we could take the inverse transform. In a case like this, is fairly simple, but again, you have to go through some sort of mechanism. Or you use the initial value theorem now. And the initial value theorem is that if you have gt and gt has a Laplace transform gs, then as t goes to 0, which is an initial value, you take the limit of SGS as S goes to infinity. So for the initial value theorem, if you evaluate it in the S domain, S goes to infinity. And as we just saw for the final value theorem, S goes to 0. And again, if you apply it to here, SGS is here. And as S goes to infinity, right, you have 1 over a very large number here, which will approach 0. Look at this here, right? At t equal to 0, because this is the initial value here, t equal to 0, you have 1 minus 1, which is 0. Okay, so again, in this sort of trivial case, what is showing us is that as t, for this particular system, when you turn it on, it's going to start at value 0. It's not going to shoot all over the place. So at this point, we have two things about it. If I turn the system on, therefore, by putting a step onto it, the system it's going to start, we know it's going to start at 0, and it's going to end, this is 1. The final value is going to end at 1. So it's starting at 0 and ending at 1. We're not too sure what it's doing here as yet, right? It could be doing all kind of things, but at some point in time, here at t getting big, it is settling at a value of 1, and at t equal to 0, the value is 0. And we could do all of that now, treating by just looking at what this system transfer function is without having to find the inverse transform. Yeah? So what I'm going to do, have a look at this one now, right? And you kind of try this now while we're here. So here's one. We have a system whose overall transfer function is this, s plus 3 over s squared plus 5s plus 4. And y is equal to some gsxs, right? So what is yt for this particular one? So assume for this one, assume that xs is equal to 1, right? So find yt for me, and then having find yt, find what the steady state value of yt is, and then if xt is a unit step that is 5 units big, what is the steady state value of that system? All right, so grab some pencil and paper or whatever you have available, and let's spend the next few minutes trying to figure this out. Right, it will put everything together, and we're kind of doing a couple of things in one here. Okay, so take a few minutes, and then I will start asking, well, in terms of the answers and so on that you have to get. This is very trivial, very easy, but it will kind of cement everything here for the class. All right, so you have a couple of minutes here. I will have to edit out this. I'll keep quiet for a little while you all work. If you have any questions, ask me. When I get the recording, I'm going to have to edit out some quiet time here, but I'll just leave the recording going while you all are working on this. So this shouldn't take more than, let me see, to do this, bim, 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 maybe 5-6 minutes. Right, you should be able to give me the answers. Okay, let's say, yeah, take 6 minutes. I'll check you back in 6 minutes, and let's see how we progress it. Try, don't wait for somebody else to get the answer or for me to put it up. Try it. If you're running into problems, then just say something for me. So have a shot. Time starts. Okay, so we have some answers as yet. Yeah, no. What is YT? Anybody has an answer for YT as yet? All right, so we had, so G S is equal to S plus 3 over S squared plus 5S plus 4. YS equal GS XS. Right, so YT, right, we said YT is this with XS equal to 1. Anybody has an answer for that?
E to the minus 40.
YT is?
E to the minus 40.
Okay, I'm seeing e to the minus 4t. Anybody else has anything? Right, remember the step is, so if XS is 1, we're saying that YS is equal to S plus 3 over S squared plus 5S plus 4.
Sorry, I make a mistake. I thought that was S plus 1. Is not e to the minus 40, it's 2/3 e to the minus t.
Okay, so you're now saying
Yes.
2 e to the minus t.
Yeah, I make a mistake. I thought that was S plus 1 before.
Okay, so let's see. Anybody else has a different answer? Okay, so if YS is this is S plus 3 into S plus 1.
It's e to the minus 40, 1/3 e to the minus 40.
Sorry, Amir?
1 over 3 e to the minus 40 plus 2 over 3 e to the minus t.
1 over 3.
3 2 to the e to the minus 40 plus 2/3 e to the.
Right, so this is a final answer, right?
Yeah.
Okay, right. So yeah, so these two were wrong. Anybody else got this?
Yes, sir.
Yes, sir.
Right. Right. So the approach, of course, was this, and then you broke it up in their partial fractions, and then you solve for A and B. Right. Okay. So what is the steady state value of this? If YT is this, which is correct. So if YT is this, the steady state value of this is YT as t going to infinity here. And what that will be? If t goes to infinity, where is that going to be?
0.
0, right? So the steady state value of YT is t equal to 0. What about the last part? This bit now. So we now have that xt is a unit step of 5 units, right? So xt is this. So if xt is that, xs is what? Xs is, if xt is something looking like that, xs is what?
5 on S.
5 over s, correct, right? So what is the steady state value now? Applying the final value theorem, what is the steady state value for this?
15 on 4.
Right, so we have t steady state is 15 over 4. Everybody got that? It is, again, it will be SGS as S going to If it's steady state, S going to 0 or infinity?
0.
Right? So S going to 0, and this will be S, and GS is S plus 3 over, well, we already added factorize, S plus 4, right? It's S by this, and the input is 5 over S. Okay, and if you do it correctly, you're going to get 15 over 4, 3 and 3.75. Make sense? Yeah?
Yes, sir.
If I had asked you to do it the long way, what would have been the approach? If instead of doing it the final value theorem way, what would you have had to do here? You would have now had S plus 3 over S plus 1 into S plus 4, right? And you multiply this by 5 over S. So YS would be equal to that. And you would now have to find the inverse transform of this. So it would be something over this, plus something over this, plus something over S. And then you solve for those three coefficients now, and then set T equal to something very large and see what happens. And you should get, because it's a fairly trivial problem, you should get the same 15 over 4. Okay, just for your own, just to get the and for you to remember how to keep doing it and so on, because you haven't done it for a little while, you should probably try that. So get YT when XT is a 5 high unit step. Do the inverse, get YT now and set T to infinity and see if you get the same 15 over 4. All right? So everybody fair with that? 2/3.
Excuse me.
Yeah.
Can you just go over the part 3 in the question, please?
Okay. So part 3 in the question asks, what would be the steady state value in response to a step change of 5 units at the input? So a unit step is something that goes from 0 to 1. So a unit step, sorry, not a unit step, a step change that is 5 units at the input means that it's going from 0 to 5. So this is what XT looks like, right? In other words, XT is 5UT, where the unit step is 1, yeah? So if XT is 5UT, then XS is going to be 5 over S. In other words, 5 by the Laplace transform of UT, which is 1 over S. All right? So what we now have is GS, which is what I just gave you here, and XS, which is now 5 over S. And from the final value theorem, we said, kind of jumping down here now, the final value theorem as T, if you want to find what YT does as T goes to infinity, that is the same as finding out the limit of S times GS as S goes to 0. SGS, remember GS is this bit here from the previous slide. So you multiply that by S and then set S going to 0. Right? So these two S's cancel out. And then if S goes to 0, you have 15 over 4. Right?
Okay, understood, sir. Thank you.
Right? And what I was saying is just again, just to remember, or to just keep that kind of the tips of your fingers, do it the other way. Try to find YT. In this case now, if YS is S plus 3 well, 5 into s plus 3 over s into s plus 1 into s plus 4. Find out what yt is and solve it. Once you get what yt is, let t go to infinity and see if you get the same 15 over 4 here. All right?
Yes, sir. Understood. Thank you.
Okay. All right, so that's it for today's class. And tomorrow now we're going to start our discussion on something called convolution. All right, which is a little bit unusual, but not too difficult. It's something that we're going to make use of some of the things when we spoke about if you take a signal and you shift it in time or you flip it around in time, those kind of things going to come into play as we go through and try to figure out what convolution means and how do we go about evaluating the convolution expression. Okay. All right. So if that's it, I'll stop the recording. Any other questions right now?